Hi, let's take a look at calculating all of the information that we can from an RLC series circuit. Now the order I drew the components doesn't matter, it's just called RLC by convention. It's what we usually do. So we have a power supply, and our power supply is putting out a voltage of 45 volts times the sine of 2 pi times 60 hertz times time. So it's a sinusoidally oscillating system with a frequency of 60 hertz, and if the frequency is 60 hertz, omega, which is 2 pi times the frequency, is going to be 377 radians per second. Now the resistor is 750 ohms. The inductor has an inductance of 1.3 henries, and the capacitor has a capacitance of 6.7 microfarads. So there's a resistance and two reactances in this circuit. Our resistance is just 750 ohms. That's always going to be there in this circuit, even if we had a situation where the capacitive and inductive reactance canceled itself out. Now, at 60 hertz, our inductive reactance is our frequency omega times the inductance. So we have 377 radians per second times 1.3 henries, which means we have 490 ohms of inductive reactance. Also means, too, that the henry has units of ohms times seconds. Now, the capacitive reactance is 1 over omega c, which would be 1 over 377 radians per second times 6.7 times 10 to the negative 6 farads, which gives me 396 ohms. It also means the farad has units of seconds per ohm. Now, inductive and capacitive reactance are the inverses of each other. They fight against each other and partially cancel out. So if I take XL minus XC, that gives me a difference of 94 ohms. So my total reactance, or my total impedance, the combination of resistance and reactance, Z, is the square root of my real resistance squared plus my net reactance squared, which gives me 756 ohms. Just a little bit above the 750 ohms of real resistance that we actually have, which means we're probably really close to the resonant frequency of this RLC circuit. Now, resonance, the maximum current that we can get in this circuit, happens when the inductive reactance totally cancels the capacitive reactance. So if I make omega times my inductance equal 1 over omega times my capacitance, that means omega squared needs to be 1 over LC, and omega is the square root of 1 over LC, which is the resonant frequency of an LC circuit. So, for our resonant frequency in hertz, it would be 1 over 2 pi times the square root of our inductance, 1.3 henries, times our capacitance, 6.7 times 10 to the negative 6 farads. And if you take a look at the units, ohms seconds times seconds per ohm, the ohms cancel, we get seconds squared, square root of that, we would get 54 per second, which is 54 hertz. So, with the impedance that we have at 60 hertz, what current are we going to see? Well, our maximum current is the voltage from our power supply, our maximum voltage of 45 volts, divided by our impedance Z, which we said was 756 ohms. So that means the current in this series circuit, which is shared through all of those elements, would be 0.0595 amps, 59.5 milliamps. So to find the voltage amplitude on each one of those components, well, our voltage amplitude is going to be the current times either our resistance or our reactance, depending on what component we're looking at. So for our resistance, the voltage on the resistor is our current times our resistance, which is 44.6 volts. Almost the same as the voltage that we have from our power supply, but we're also pretty close to resonance. Now for our capacitive and inductive reactance, the voltage on our capacitor is going to be our current times our capacitive reactance. So I have 59.5 milliamps times 396 ohms. That gives me 23.6 volts. And for the inductor, it would be my current times my inductive reactance. So it would have 490 ohms times my 59.5 milliamps, which gives me 29.2 volts. Now the final piece of information that we can pull from this example is what's the power angle? What's the difference in angle between our voltage and our current in terms of phasor diagrams? Well, if it's 90 degrees, there's no power delivered. If it's 0 degrees, we're at resonance, there's full power delivered. We're going to be a little off from 0. So the way we do that is using the Pythagorean sum of our net reactance, which is 94 ohms, combined with our real resistance, 750 ohms. Our impedance is the hypotenuse of that Pythagorean sum. The power angle is going to be based off the tangent, which is 94 ohms divided by 750 ohms. So if I take the inverse tangent of 94 750ths, I get an angle of 7.14 degrees. Thanks for watching.